All right, so we're going to continue looking at section 6.3, and this is 6.3, part 2. Okay, in this section, we're going to look at the stretches. So stretching left and right, stretching or compressing up and down. So the first thing we're going to talk about has to do with the height of a wave. So if we look back at this picture, you could almost draw, let's do it by hand, but you could draw like a center line right there. And then you could measure the distance from that center line up to, and if they were all equal, then this would have, it would be a little easier. They're all a little different, just the way it picked the microphone, picked it up. But that height from the center of the wave to the top of the wave, that is called the amplitude. So it measures the distance from the center to the peak, and it is symmetrical from the center to the low point. Okay, so the amplitude is measuring a distance. And when you think about numbers that represent distance, distance is always what kind of number? Yep, it's always positive. We don't really talk about distance being negative. So in a minute, I'm going to write something down about amplitude and the fact that it's always a positive number. And what can we do in math to make sure something is always positive? There's like an operation we can do to a number. And that's going to come up here.
Absolute value.
Yep, absolute value. So that idea will come up in a second. So when we want to change the amplitude, changing the amplitude would look something like this. Let's graph sine x, and let's put in 3 sine x. Okay, now that doesn't look good. It doesn't look like a wave, because there's something I said you should always do first. I said this yesterday, and I didn't do it here. What do we usually want to do first on the calculator? Yep.
We want to change something to trig. Oh, the zoom.
The zoom.
To trig.
Yep. You always want to do zoom 7, and that'll set the window properly. Okay, so there's your sine function. And there is a sine function that has exactly the same distance between the peaks, but the peaks and the valleys are higher and lower. Okay, that's what we call a change in amplitude. And anytime that we multiply, that's stretching or compressing. Specifically, if you multiply by a number in front, that's what we call a vertical stretch. Just like every function we've studied all year. Multiplying by a number in front is a vertical stretch. If you want to know how much of a vertical stretch did you do, how much did you change the amplitude, what is the new amplitude? You take the absolute value of the number in front. Now, if I did something like this, I'm not saying that the negative isn't important. If you're going to graph it, the negative does something very important to the graph. But if all I wanted to know what the amplitude was of this function, it is 4. The amplitude of this function is also 4. The negative has no effect on the amplitude. But can somebody remind me, what does a negative do when you graph something? Yeah?
Doesn't it shrink the graph?
Whether it stretches or shrinks is going to be dependent on how big this number is. But the negative does something else. Yeah? It flips. Okay. If you take a graph and you flip it, think about what that would do to the amplitude. There's your graph, and you flip it. So you know what? I can flip it exactly just by going like this. Well, it's not perfect, but you get the idea. How did flipping it change the amplitude? Just flipping it. You know what? It didn't. Okay, flipping it has no effect on the amplitude, but it does have an effect when you draw it. Okay, so the negative is important when you're making the sketch, but not when you're just finding the amplitude. So amplitude is always a positive number. So an amplitude change is going to either stretch or compress the graph along the y-axis. What kind of numbers do you think are going to cause it to stretch versus compress? Yeah?
Numbers that are greater than 1 and less than 1.
Greater than 1? Okay, let's think about that like on a number line. Let's kind of mark this. So here's 0. So you're saying if you're in the greater than 1 section, what's going to happen here?
Oh, I think it was an amplitude.
Yeah. So what if you plug in a number for the amplitude, like the C value, that's bigger than 1? What did you say is going to happen?
It'll get larger.
Okay, so it's gonna stretch. And what else did you say is going to happen?
Between 0 and 1, it'll get smaller.
Okay, so between 0 and 1, we're going to get compression. Okay, what about the other way? Yeah?
If it's -1 or lower, then it'll flip it and also stretch.
Yep, so that's going to cause a flip, but it's also going to cause a stretch. And what about between -1 and 0? Yep.
It's also going to compress.
That's also going to compress. Yep. So I can just actually label this whole thing compress. So this is showing what's happening depending on the value you plug in for the number in front. If you plug in a number bigger than 1, it stretches. If you plug in a number smaller than -1, it stretches. It also flips, but it also stretches. If you put in a number between -1 and 1, that will cause it to compress, like 0.5, 1/3, -1/2. -1/2 would cause a compression and a flip. But I'm just trying to show you what kind of numbers make it stretch and what kind of numbers make it compress. Question?
Can the amplitude be 0?
No, so if the amplitude was 0, then all you basically have is a straight line. You wouldn't really have a trig function anymore. Because think about what happens if you multiply by 0. What's 0 times anything?
0.
So now all you have is y equals 0, which is just a horizontal line at 0. So we wouldn't technically consider this a trig function anymore. So no, I've never heard anyone referring to the amplitude as 0 and still calling it like a sine wave. Okay, so here's the same thing. I thought I wrote it out. Or did I write it out on the next page? No. Okay, so let's find the amplitude. So here's our function. And over here, put the amplitude. What would the amplitude of 3 cosine x be? Yep.
The amplitude is 3.
The amplitude is 3. The absolute value of the number in front is the amplitude. So in that case, it's 3. All right, how about that one? That says 4/3 sine of x plus pi over 2 plus 6. What's the amplitude there, yeah?
Would it just be 4/3?
Just be 4/3. There's some other things happening there that we talked about yesterday, but none of those affect the amplitude. Shifting left and right doesn't affect the amplitude. Neither does shifting up and down. You might say, well, wait, if you shift it up, would the amplitude be higher because it's up higher? No. If you shift it up, the graph would have a higher maximum value, but it wouldn't have a higher amplitude. If you take a graph like that, you just copy it, and then just shift it up. The amplitude is exactly the same, because the amplitude is kind of, imagine a center line right through the middle, and then you measure the distance from that center to the highest point. It's exactly the same in both. The difference is, if I said to you, what is the maximum, and you used your calculator and did like second calc maximum, you could find that this one might be at 1, this one might be at like 6. So it has a higher maximum, but not a higher amplitude. So just focus on the number that you need to. Okay, how about this one? -2 sine x. Would be my amplitude. 2. Yep. That one would be 2. What if I did this? What's my amplitude now? Yep. 2. Still 2. What if I shifted it up 4? What's the amplitude now? Yep.
Still 2.
Still 2. The only number that would affect the amplitude is if I changed this one, the 2. Nothing else I did there made a difference. That's what it was originally. So on the test, you will have a couple questions that are non-graphing, and all you have to do is look at an equation and write down what the amplitude is. You just click on a box, type in the number, and that'll be it. Or it could be a multiple choice or something like that. Okay, so any question on how to find the amplitude? Okay, so that's finding the amplitude. Now, let's think about how we're going to draw the graph. We're stretching or compressing it up and down. If you take a point and you move it up or down, what part of the coordinate is affected by that? The x part or the y part? Yeah?
The Y.
The y. So when we want to do our graphing, the y's, or the x's, are going to stay the same. The y's are what are going to change this time. So now we're referring back to that original table we made yesterday. We're going to copy down the column that stays the same, which in this case is the x's. And when the x's stay the same, that's good, because the x's are harder to work with. Those are all the fractions with pi. So a lot of times to work with the x values, you have to find common denominators and all that stuff. But this time, we don't have to worry about the x's. So the x's stay the same, then it's the y's that are going to change. Okay. Very, very simple change. All you have to do is take the old y values, which are the ones that are in the table I gave you yesterday, and multiply them by the number that's in front of the function. Notice there I did not put the absolute value of the number. You use the number the way it is, because if it's a negative, that's important. It's going to cause the graph to flip. So do not take the absolute value when you're graphing it. Just use the number the way that it is. So we'll try a couple examples, making the table and then doing the sketch. But first, I'll play for you what that would sound like. So comparing a sound like, where is it? There it is. Basically comparing two sounds like that. I think I already said what it would sound like, but does anybody remember? If we stretch or compress it vertically, what's that going to do, like the red sound versus the blue sound? What would the difference be? Yeah?
The red sound will be louder.
Yep. It has to do with, when you stretch or compress a wave vertically, it has to do with intensity. How we perceive intensity with a sound is louder and softer. Light can also be modeled with a wave. when you change the intensity of light, it doesn't get louder and softer, it gets brighter and darker. So whatever type of wave you're dealing with, its intensity, however you measure that for what you're modeling. So if I play an example, you can hear what it's like. What I'll do is I'll actually use the microphone to pick up the sound, and then you'll see an actual picture of what's happening. Okay, so there's that. Let's put that there. There's over here. You can see the wave. And it gets louder. You can see it's starting to stretch. And as it got quieter, I didn't show you, but as it got quieter, it would compress. Okay? And I was going to take a picture, but it actually wasn't that interesting. For about 3 seconds, you heard two frequencies at the same time. It was the frequency of the bell, and then there was the frequency of what I was playing. And they kind of interacted a little bit, but the bell is a lot further from the speaker than this is, so I think this sound overpowered it. But if they were the same volume reaching the speaker, you would have seen kind of a interesting picture. And if we have time after, maybe I'll play two sounds at the same time, and I'll show you what they look like on this program. Okay, we'll see if we can do that after. Okay, so let's graph 3 cosine x. Okay, so we've studied horizontal shifts, vertical shifts, and vertical stretches, or amplitude changes. Can anybody tell me, out of the 3 we've studied, which one is this one? Yep. Yes, we know it's an amplitude because 2 things. 1, it's multiplication. 2, it's in front. So when we do amplitude change, Quinn, what values stay the same?
The x's.
The x's. Can you remind me what my x's are?
0.
Yep.
Pi over 2. Pi. 3 pi over 2. And 2 pi.
2 pi. Good. Okay, so the way that a table like this is graded, for those that weren't here yesterday, there's going to be 10 numbers in this table when we're done. You get 1 point for each number you get right. Okay, I still need to do my y's, but before I put in the final answers, I'm going to put the original y's off to the side. Sam, what are my original y's for cosine?
1.
Yep.
0. -1. 0. 1.
And 1. Okay, so there's my original y's. And now, Aiden, what am I going to do to all these y's to get my final answer?
Multiplying by c.
Yep, and what's c in this case?
3.
3. So we're going to multiply these all by 3. Perfect. So we get 3, 0, -3, 0, and 3. Out of the 2 transformations we're going to do today, this is the easy one. Okay, the arithmetic is much simpler than working with the x's. But any questions on how we got that table? Okay, now to graph it, well, the bigger you make this number, the taller and taller the graph is going to get. But we don't, if we made it like 40 or 50, we don't want to have to draw this 40 or 50 times as big. We're gonna run out of room on paper. So what I'm going to do instead is I'm going to scale my axes. Since I need to go as high as 3 and as low as -3, I'm just going to scale my y's to go like this. That's how I would do it. And then for your x's, 0, pi over 2, pi, 3 pi over 2, 2 pi. And now plot all your points. So 0, 3, pi over 2, 0. Pi, we're at -3. And then we start going back up. 0, and then back to 3. And I mentioned yesterday that it looks kind of like a V shape, but there's nothing in these pictures that should have a point in it. Okay, they should always be a smooth curve. Just sketch it best you can. That's okay. And that's a sketch. So every cosine graph I do today is going to look the same. The only thing that's going to change is these numbers. Like if I had to graph, let's say, I don't know, 35 cosine x. The only thing I would do here is this. Now you're looking at a graph of 35 cosine x. So the picture doesn't change. The scale on the axis does. Then I don't have to draw it 35 times as big. Any question on that idea? That's it. That's your sketch. Same idea with sine. I'm going to scale my axes, so no matter how big or small it says to change the amplitude, the picture always looks the same. Okay, so Max, what arithmetic are we doing in this problem? Is this an addition or subtraction, or does this one have multiplying? This is multiplication. Multiplication is always a stretch. Oh, Eli, where is the stretch? Is it, or where is it, the multiplication? Is it in front, or is it next to the x?
It's in front.
It's in front. When it's in front, that means it's a vertical stretch. Okay, Lucas, vertical stretch, what stays the same?
The x's.
X's. Again, if you weren't here yesterday, we talked about where these came from. So those are your original x's. Okay, my original y's. Maddie, can you tell me what my original y values are? And just make sure you give me the ones for sine.
The -2 or 5 one? Start with the,
No, it doesn't start with -2 or 5. I'll give you a hint. It looks like this when you draw it. And we're looking for the y values.
Start with 0.
Mhm.
Alright, 0, 1, 0, -1, 0.
Very good. Oh, I didn't mean to put those there. Sorry. I meant to put them off to the side. So those are my originals. And now, what are we going to do to each one of them?
We're going to multiply them by a half.
Yeah, multiply by a half. Some people say divide by 2, and same thing. Okay, so multiply them all by a half. So we get 0, half, 0, -1/2, 0. Now, I said to you, you usually don't use decimals. If you put 0.5 and -0.5 here, that's fine. When I'm talking about not using decimals, I mean don't put 3.14 here. You're going to get that wrong. Okay, so the x column is the one that usually has pi in it. And every problem we've done so far, it has. And there's your table. Okay, the highest and lowest I need to go this time is 1/2 and -1/2. So if you want to scale it that way, you can. I mean, 1/2 isn't really compressing it that much. You really, I guess you could leave these as 1 and -1 and draw your points not on the lines. But I like my points to end up on the grid lines. Just makes it easier. Okay, so 0, pi over 2, pi, 3 pi over 2, 2 pi. Right. So use those x values and start at 0 and go through all the y's. So we've got 0, 1/2, 0, -1/2, back to 0. That's the one most people don't mess up sketching because they see more of the wave in it. It's the cosine one, when it looks like those 5 dots that are in a V shape. They don't sketch it as a wave sometimes, but remember, it's a wave. It's just the V part, not the S part. Same. Hey, questions on that one? All right, what's the amplitude of this one? I didn't ask that. Yep. 1/2. And this one? 3. And this one? Yep. 1. This technically is not an amplitude change. But the way we do the arithmetic in the table for this problem is just like it was. What's going to happen in this problem? The amplitude is 1, so it's not really changing or stretching. It's not stretching. Yeah?
It's gonna flip.
It's just going to flip. So the x's stay the same. And the original y's are 1, 0, -1, 0, 1. That would be a really good thing to put on a reference sheet for the test. And we're going to multiply them all by -1. So they're basically all just going to flip from positive to negative. Or if they're 0, they stay the same. So -1, 0, 1, 0, -1. So there's your table for that one. As far as scaling the y-axis this time, I wouldn't change anything. I would just leave this 0, 1, -1. That's perfect. But the x's we do need to label, because I am not going to go by ones. 0, pi over 2, pi, 3 pi over 2, 2 pi. Okay, so let's see, we're at 0, -1. So left and right 0, down 1. Pi over 2, we're at 0. Yeah.
So if there's nothing written, that every line is an increment of 1, or do you
Yes.
think we should add it just anyways?
It's up to you. I always assume if you don't label it, you're going to go by ones. That's pretty standard. So it's up to you. Pi, we're at 1, 3 pi over 2, back at 0. 2 pi, back at -1. So instead of looking like a V shape, this one has been flipped over and it's more like an N shape. Like that. Any questions on that? All right, so stretching and compressing vertically changes the volume. Not the most interesting, but you can hear it. Okay. Period changes. Well, period changes are going to be a stretch or compression, but they're not going to be vertical. They're going to be horizontal. So every graph that we've studied so far has had a certain distance to go through one cycle. Does anyone remember from yesterday what this distance is from the beginning to the end? You have to go through how many degrees or radians? We usually are using radians, but you have to 360 degrees or 2 pi. So the length of one cycle or one period has always been 2 pi radians to go through one full wave. Well, now we're going to change that. We're going to stretch or compress it. And knowing what the standard period is going to help you to figure out the new period. So like the last type of graph, I'm going to ask you a question on the test that's not a graphing problem. It's just going to be a question about looking at the equation. except we're not going to look at the amplitude this time. We're going to look at the period. Since a period change is going to stretch or compress horizontally, that's all it is. I know we haven't called it a period change before because we weren't dealing with sine and cosine, but it's just stretching and compressing horizontally. Whenever you stretch, it's always multiplication. How is this multiplication different than an amplitude change? Still multiplication, yeah?
It's at the end.
Well, if we put something at the very end, like plus or minus, that's usually like a vertical stretch. So it's not at the very end, but we're on the right idea. Where is it? That is the thing. Yep. It's in the parentheses. It's like a phase shift. With a phase shift, which was moving left and right, it had to be in parentheses with the x. Same idea here. It's in the parentheses with the x. Now, if b was negative, that does cause a reflection. But for this one, we're not going to look at reflecting horizontally. So we're only going to look at examples where the b is bigger than 0. So you will not have to worry about a reflection horizontally. We could, but we're not doing it. Yeah.
Say there was like cosine x, and then it was like times 3 on the outside. Would that still be an amplitude change? Would that be like vertical stretch?
Cosine x
That's
times 3.
outside, like outside the parentheses. Yeah.
Like that?
Yeah.
Well,
I mean, it would be written wrong, but would it do the same thing?
if you write it like that, you got to follow PEMDAS.
Yeah.
You got to follow your order of operations. And order of operations would say to do the trig function first and multiply by 3 after. So effectively what you wrote there is this. That would be like that. Because you're always supposed to do your trig function first and then multiply by 3. So that would actually be the same as that. I would never write something like that on the test. But no, this would not be a period change. Now, if you did this, that's kind of a weird way to write it, x3, but yes, that is a period change. Because when you multiply, the order you multiply two things in doesn't matter. 2 times 5, 5 times 2. And it is in parentheses with the x, which means order of operations. You do what's in the parentheses first, and then you do your trig function. So that would be okay. Does that answer?
Well, I was asking if, I mean, it did, but I was asking if 3 was at the end, if it would be an amplitude change, not if it would be like.
Oh yeah, it would be an amplitude change that way. Yeah. Okay, so we're looking for the number that's inside, and it will always be in front of x. So period change is going to stretch and compress the graph horizontally. Let's look at an example. Let's say I do sine x and sine 3x. What do you think is going to happen with the sine 3x? Is it going to be stretched out compared to the original? Or do you think the 3 is going to cause it to compress? Yeah?
Stretched out.
Think it's going to be stretched out? All right, well, let's see. It's one of the two. So there's the original. And the one that's in red is the 3x. So what happened? Did it stretch out or did it compress? It compressed. The distance between, if you just look at the cycle, here to here is one cycle length of the blue one. Just look at the peak of one and the peak of the other. Now look at the red one. There's a peak there, there's a peak there. That's a much shorter cycle length than it was originally. And you can measure the cycle length from anywhere, you just have to be consistent. If you measure it from the peak of one, measure it to the peak of the other. The bottom of one to the bottom of the other. It's the same. Okay, but it compressed it. So the bigger that you make B, the more compression you get. smaller that you make b, the more of a stretch you get. So like 1/2 would stretch it. 1/4 would stretch it even more. The closer the number gets to 0, the more stretched out it gets. So it's kind of the opposite of what you would think. Bigger numbers compress it smaller. Small numbers stretch it bigger. And what do you think the difference would be with sound with this one? Like the blue sound versus the red sound. They'd have the same volume. Whether or not you can hear the same volume, well, we'll get into that. But they wouldn't have the same amplitude. Yeah.
You have like different pitches.
Yeah, they have a different pitch to them. So let's try a few examples of that and see what it sounds like. Okay, so I told you one type of question we'd look at involves just finding the period, not even doing a graph. So to find the period of a sine or a cosine wave, you take the original period, which is 2 pi, and you divide it by b. B is the number in front of x. B is not the period, just to be clear about that. This is the period. 2 pi divided by b. B is just the b. So let's try a couple examples where we don't have to sketch anything. All we have to do is find the length of the period, which is the distance through one cycle. So just remember that formula. 2 pi divided by b. Here's our first. Sine 2x. First of all, what is b in this one? Yes? 2. So you just fill the 2 in for b. And you get t equals, I don't know why they use t for periods. That's what they use. So the period is 2 pi. The top part never changes. The bottom part is what you fill the number in for, and we fill in 2. And what's 2 pi divided by 2? Yep. Pi. Is this period bigger or smaller than the original? Yeah, smaller. And that's exactly what should happen. The bigger you make this number, the more compressed the period gets. So the period there we would say is pi. Let's look at this one. So the period is 2 pi. And what are we going to divide by for the b value in this case? 1/3. Now, when you divide something by a third, what does that really do to it? You're dividing by something less than 1. It gets bigger. And specifically, dividing by a third would multiply by 3, right? That's what we've always learned. You have to divide by a fraction. You keep the top the same, and you flip the bottom and multiply. So what's 2 pi divided by 1/3? Yeah? 6 pi. So in this case, the period got much bigger. It got 3 times as big. That means the wave would have stretched out 3 times as much. All right, let's look at this one. Sine of pi x. To find the period, what number goes in the top? 2 pi. And what number goes in the bottom this time? Yep. Pi. That gives me a period of 2. It's the first time we've ever seen a period that doesn't have a pi in it. But that can happen. And what's the period of 2 sine 3x plus 2? A lot of other numbers there, but you only have to focus on the one that's important. Yep.
2 pi over 3.
Yep. Stretch stretching up and down, shifting up and down does nothing to change the period. So it's 2 pi over 3. So we're stretching and compressing left and right. What part of a coordinate changes if you stretch and compress it left and right? Does it change the x or the y? It changes the x. So when we're finding the new points in our table, the x's are going to change. The y's stay the same. Unfortunately, the y's are the easy ones to work with. We can't work with them this time. So we're going to have to work with the x's. But it's a pretty easy calculation that you have to do with the x's. All you have to do is take the original x's and divide them by b. Okay, divide them by b. Now, in the case of dividing by a fraction, that would really mean we could switch it to multiply. But we'll look at that. So take your original x's and divide them by b. Y stay the same. Okay, so we'll try 1 or 2 with period change, and that'll be it. Sine 1/2 x. First thing is to look at it and say, okay, what is it? Is it a phase shift? Is it a period change? What's happening? It's multiplying inside. Multiplying inside, period change. What stays the same when you're going to stretch or compress left and right? That's period change. The y's. So hopefully we're starting to get familiar with those. Those are my y's. Put the original x's off to the side. And the directions say take the original x values and divide them by b. So what are we going to divide every one of these by? Yep.
2.
We're going to divide them by 1/2. That's my b. Now, dividing by a fraction, that's a little confusing to me. So instead of dividing by 1/2, that's the same as multiplying by what? 2. If it wasn't a fraction, then I would have just done division, because division when it's not a fraction is easy. But when it's a fraction, it's easier to think of dividing by a fraction as multiplying by 2. What's 0 times 2?
0.
How about pi over 2 times 2?
Pi.
Pi. Pi times 2?
2 pi.
2 pi. 3 pi over 2 times 2?
3 pi.
3 pi. And 2 pi times 2?
4 pi.
4 pi. And that's it. Those are your new x values. So this time you don't have to scale the y's. You can just leave those as 0. Fill in the 1 and -1 if you want. But label your x-axis. 0 pi, 1 pi, 2 pi, 3 pi, 4 pi. This is not going to look stretched because I changed my scale. Because if I scale it really big, I don't want to have a really big piece of graph paper.
Are the x values just gonna increase by the same increment every single time?
They have to be the same increment, yes. Always.
So if you figured out like the first 2, would you know what all the ones are after that?
If I was doing it, yes, I would. Yep. So once you figure out the first one, they're all the same after that. But some people don't see that pattern as easy, so yeah, if you see that pattern, that speeds things up a little bit. And there's your graph. It doesn't look stretched because I changed my scale. Okay, questions on that? Okay, let's try this one. Cosine 2x. Now the number in front is not a fraction, so that actually makes it a little easier to work with. X's are going to change. Y's are going to stay the same. What's that?
It's not in parentheses.
So with order of operations, that 2 is still with the x. Even if it's not in parentheses there, this 2 and x are stuck together. It's kind of like if you wrote like 2x plus 3x in math, or you wrote 2x plus 3x. It doesn't matter if you put parentheses here or not, it's still going to be 5x, even without parentheses. So it's still going to be 2x, even without parentheses. But you could put them in if you want. It just has to be with the x. Okay, so what are we going to divide all these by this time? Yep.
2.
Divide them by 2. Dividing something by 2 basically means to take half of it. So just take half of all of these. What's half of 0?
0.
Half of pi over 2?
Pi over 4.
Pi over 4. Half of pi?
Pi over 2.
Yeah, half of pi. What's half of 3 pi over 2?
Is it just... It's probably wrong, but is it 3 pi over 4?
Yeah, you just think about multiplying each one of these by 1/2. I mean, you could think about dividing it by 2, but sometimes it's easier to think about just multiplying by 1/2. It's the same thing. And how about the last one? What's half of 2 pi?
Pi.
Pi. So those are your x values. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. Of course, we don't write 4 pi over 4, that's the pattern, but we reduce it as much as we can. Okay, so we've got 1, 0, negative 1, 0, 1. And there's your sketch. So the key to remember this time is you are changing the x's. You divide them by b, or multiply them by when you flip it, whichever way you want to think about it. Okay, so I think there's one question you didn't get to, but it was just another period change. We could do that one tomorrow. Okay, so that's the homework for tonight. Again, those that weren't here yesterday, we are not doing the worksheet that's on Schoology because that was a little different. Okay, so those are the 8 questions for homework tonight. Okay, and I'll put that up on YouTube as well.